So first video of Unit 4, we're talking about similarities and proofs. So similarities is different than congruent. Congruent was the idea, and that's what we did a lot of in Unit 3. It was talking about theorems, but mainly it just wanted us to get used to proofs. But the main concept we kind of proved there when we were doing proofs was congruence. Congruence is all the properties are pretty much equal. The lengths are equal, the angles are equal. The difference between similarities is this idea that it's the same angles, it's the same shape, everything's the same except for the size. It's smaller. So that's why we're going into properties of dilation. We're going into this idea of what changes when everything is smaller. Give me a second because I forgot to grab my stylus. I got my board ready, but I didn't get my stylus out. There we go. All right. So let's get into this. Properties of dilation. So in this lesson, we're going to verify experimentally. So experimentally is just meaning we're going to verify it using GeoGebra. That's all it means. Properties of dilation given the center and scale factor. So in dilation, we know it as something getting bigger or smaller, but the way we're able to do that is this idea that, like, let's say we have this triangle, there has to be a center of dilation, in which case the distance becomes bigger or smaller. So let's say I'm dilating this shape right here, and this is my center of dilation. It would move if my center of dilation was outside the triangle. But if it's within the triangle, first of all, it has to be exactly in the center. And then if you're decreasing that distance, that scale factor, what ends up happening is it gets small exactly in the center. So you're cutting it, like if I were to cut this in half, if my scale factor was 1/2, it would be right in the center. So it's not just a matter of making it bigger or smaller. There has to be a spot where we're making it where our center of dilation is. Otherwise, we're not only dilating it, we're also translating it. So if our center of dilation is outside of it, it kind of feels like we're translating it, but we're not really. What we're doing is we're just cutting the distance of every point in half. So that's just an example. I know it's not drawn to scale, but you can get the idea that the distance from this point to here is 1, but then the distance from here to here is 2, and then the distance from here to here is 2, so the distance from here to here is 4. So because we're doing that, that's why shapes kind of get bigger and smaller. So let's take a look. So we're going to be talking about this advertising agency that's going to make the logo bigger or smaller depending on what page it's on, or how big they want to take up the page. So here's an example of what I was talking about, dilation. So in this one, we can probably assume that the center of dilation is over here. It's getting either closer to this point or further away from the point. So this is our actual triangle, and this is it probably twice as far away. This is probably half, and by making it further away, it just makes it closer. It just makes it bigger or smaller, sorry. And you'll always notice with a center of dilation, there's always kind of this line that would line up with it. Like all of my A's should theoretically be in a straight line that would lead up to the center of dilation. Again, for this, you don't really have to know all that it makes a line, but it just makes it an easier understanding on why things get bigger, why things get smaller. So here's the boat dealer logo, and we're going to start with dilation. So we're going to do the GeoGebra. So here we're going to see what happens here. So let's see what happens when I increase it to 2. So by increasing it to 2, notice how this line still stays on the x-axis because the distance isn't going to make it go up or down. It's literally just increasing the distance that's there. This b prime, we see, since the center of dilation is right here at the origin, we see that it gets further away, but it's still like in that straight line. It still has the same slope, if you guys remember that from algebra. All right, so that's how it is messing with it. Let's see what the problem actually wants us to do. Verify the end is less than half. How do the points differ? What happens to the logo of the sailboat as we increase the scale factor? So it wants us to do less than 1. So if we do less than 1, we see that the boat gets smaller. If we do greater than 1, our scale factor, this scale factor right here, that makes it get bigger. So we're just going to say something like that. We're just going to say if the scale factor is smaller than 1, the boat becomes smaller. As the scale factor gets bigger than 1, the boat becomes larger. And make sure you're using your own words for this, guys. Don't plagiarize, use your own words. I'm just showing you guys that you can use easier words like bigger, smaller. You can say it gets larger, it gets whatever. Whatever words you want, just make sure you're using your own words. Don't plagiarize, don't use other people's words. Again, just move my words around, use more periods, more punctuation. I'm just here to help you understand it. So now we want to look at the slopes. What's happening to the slopes of these lines? So let's take a look at that. So first things first, they want us to do it at 0.5. So let me kind of zoom in here so we get most of the boat. All right. And it wants us to find the slope of LK. So the original slope for LK. So let's click slope. Okay, where is slope? Slope. There it is. And we're going to do LK. So the original slope is 2. And then the new slope is also 2. Okay. So looks like the slope is the same. Give me a second here. Oops. For those on YouTube, you can see what the question of the day is, and you guys can answer too. All right, now let's change the scale factor to 2. Now, the cool part about me doing the scale factor on this is I believe it still shows me the slope even if I get larger. Yep, it does. So I want to make this go up to 2. And we see that the slope, let me move this around, is still 2. So the slope is still 2. So we can effectively just say that the slope is going to be the same for all of them. The slope is the same no matter what the scale factor is. And I can prove that just by doing it again. Still 2. All right. So now let's kind of just focus on the other side. So I'm going to delete these since we answered all the questions for that. One thing that I wanted to mention, some people have mentioned that it's hard to do the activity and follow along in the class. What I recommend is take notes. Like take notes of this because you can always rewatch the video later when you're doing it. but right now is a good time to ask questions. So if you guys aren't understanding anything, I do have the chat open in my other monitor. So you guys can just ask, like, wait, what was that? Like, how did you do that? That's just will help you learn it for when you have to do it on your own. So now I want to find the slope of GB. So I'm going to do slope of GB. Click slope GB, and my slope is 0. Now I'm going to go to 1/2, and I'm going to do slope again. I'm going to do GB. It's still 0. And if I go to 1 and 2, where's 2? There we go. 2, it's still 0. If I go to 3, it's still 0. So effectively, what we should be noticing is the slope does not change. And what we're going to learn later on is if the slope doesn't change, that means the angles do not change. So just to go into the H part of it, let me go back here. So now we'd have to do AH. So AH is this straight line right here. So I'm going to click slope, click AH. And one thing you'll notice when I do this, if it lets me, it's not saying what the slope is. And that's because this, I can also try this way, clicking the points. Yep. This is what's known as an undefined slope, meaning that there is no slope because there's no rise over run. So that's how come it's not showing anything. So what we're going to do for these is we're just going to say it's undefined because even if we change the scale factor, it's still undefined. It's still a horizontal line. It doesn't change. It doesn't even move. This one at least moved, but the line's still the same. So we're just going to say undefined. And what you can do too is just Control C. What I do is I use Shift as the arrow key to be able to highlight everything, and then you can just Control C from there. And then you can just use your arrows on your keyboard to go back and forth. So I'm going to Control V, which pastes it on there. And that's pretty much it. So we can submit that. Next, it's like for the scale factor N3, select the line LK and compute it. So this one, they actually want us to solve it. So let's go to our thing. We want to find LK. So if we look at LK, my points for this, let's see if GeoGebra is going to be nice to my stylus this time. Every time I do this now, I don't know what happened, but GeoGebra hates it. So our first point for L, yep, GeoGebra just hates it. Our first point for L, I'll do it over here for now, is 0, 6. And our second point, technically our first point, because we always want to go from left to right, is, what is that? I want to say that's like -3. Let me check my points right here. You can always check your points here if you have doubts. So K prime -3, yep, -3 comma 0. So my first point is -3 comma 0. Now, what I like doing when I calculate slope, I don't really like using this formula. I like going like this. How far did I rise? I rose 6. And then I go like, how far did I run? Oh, I ran 3. So I end up getting this 6/3. They want you to do the formula, and I guess that's fine. There's two ways to do the formula. You can do the formula as 6, or obviously it's a slope because it's rise over run. 6 take away 0 over 0 take away -3. And this will give you that 6 over +3, which ends up being 2. Now, let's say for some reason you're like, well, what if I accidentally put these points backwards? So if you accidentally put these points backwards, don't worry about it. Because see how this double negative makes it positive? Well, if you do it backwards, 0, -6, and you do this -3 minus 0, you end up getting this fraction of -6 over -3. And what we know about a negative divided by a negative is it's still going to be a positive. So don't worry about what's my point one, what's my point two. As long as you keep them together, it's going to be okay. One of them is down 6, left 3. The other one is up 6, right 3, which is the same thing. If I go down and left, it's the same thing as me going right and up. Or it's the same thing as me going up and right. Or it's the same thing as me going down and left. Everything ends up being the same. Or I should say left and down. The slope ends up being the same regardless. As long as you're still going by the same amounts. All right. And so I don't like negatives. That's why I chose the first way. So that's what it means by calculating it. You can also calculate it if you want by doing what I said. You just line up your points. And you can kind of, oops, not over. And you can kind of just be like 0, 6. And just show a picture of you doing this. That's fine. That's showing your work. And it is calculating it. It's just they're trying to force this formula on you. And to me in geometry, it doesn't make sense to force this formula on people. All right, so now we want to do the same thing. So question 3, are the values equal? To measure the lengths. So this one, we're going to do the exact same thing. We're going to pick 2 points and we're going to measure the lengths and see if they're equal or not equal. To me, I don't understand why they want us to do this. We already proved that they're the same. So you can pick any lines you want. I recommend just copying these lines over here. Just do this exact same lines. Why do more work when it's just repetitive work for repetitive sakes? So I'm literally just going to go, let me take this. Notice how it does a little picture thing? It's actually an equation. You can go in here and, oh, I thought you could. Apparently, Admentum's lazy and they don't even use their own equation editor. I'm going to do this, paste this there. Slope. So this is a calculation. So if it's a calculation, just do rise over run. You don't have to do the actual formula, just do your rise over run. So if we're doing GB, GB is 0 over, what is this? This is 2 all the way to 3. So 2 all the way to 3. So that's a run of 5. So 0 over 5. 0 over 5, which ends up being 0. Is it equal? Yes, it is equal. So I'm just going to put an X here to show that's equal. And then we're going to do AH. So I'm just going to copy this AH. Like I said, you can do it with other things. It's just, I feel this is repetitive and there's no sense in doing this. If we're doing AH, what is my rise? My rise is from A. So this is like, what is my A? At A, it's like a half. And then H is 2.5. So it ends up being a rise of 3. If you go up 3 from negative a half, you're going to go to 2.5. So rise over run. What's my rise? I'm going to say, and you can do something like this too, 3 over 0. It's a fraction. That's fine. It is equal. They are undefined. So if we calculate it with GeoGebra, we said undefined for AH. GeoGebra said this was 0. And that was our GB. And we're going to say that they're both equal. Because 0 is the same thing as 0 divided by 5. You cannot divide by 0, so it's called undefined. In general, how do the slopes of the line segments compare corresponding to the line segments of the pre-image? Is there any difference? So we're just going to say the slopes are the same after dilation. So after dilation, the slopes remain the same. What effect? The scale factor does not affect slope. Minor English lesson here. An effect is something that you can see. Affect is a verb. So an effect, noun, affect is verb. How is it affecting it? It does not affect it. What does the relationship between slopes and corresponding line segments of the previous stream? In other words, what do you know about two or more line segments that have the same slope? So if two line segments have the same slope, they are dilations of each other. So if they have the same slope, there's some number we can multiply a line by, even if it's a weird number. So let's say I had a line, this is 2, and then this one is 3. The way you always do this is you always do the scale factor as new divided by old. So in this case, the scale factor would be 3 over 2. If I had this line here, this line is, I don't know, 1.5. And I have this other line over here that's 9. Then my scale factor would be 9 divided by 1.5. That's how you always find scale factor, new over old, including if you have something like this, 6 and 2. So let's say this was my original line. My new would be 2 and my old would be 6. So my scale factor is 1/3. What's the scale factor? Oh, it got smaller. The scale factor is 1/3. It's smaller than 1. Is this making sense, guys? The whole new over old? That's how I taught it out of the packets. Just remember it as new over old. I think the packets call it, what do they call it? I think they put, instead of old, they call it original over magnified. I don't really like the original over magnified because technically you can make something smaller. But everybody get this? The new over old? Yes, no, maybe? Anybody awake out there? Cool. Thanks, Alec. All right, so now we're going to recall the center of dilation with point J. So center of dilation, again, that's where we're growing from. So that contain the center of dilation that do not contain certain scalar dilations. Record the names of the line segments and the categories they belong to. What differences do you notice in the ways these line segments are mapped? So it's just saying that, like, let's say a line does have the center of dilation. And there's one that it doesn't. So, like, the sail, remember, it just went away from it. And there's also, okay, so contain the center of dilation, do not contain the center of dilation. That lie on a line that passes through the center of dilation. Okay, so I kind of get what this is saying. It's saying that, let's say there's a point that is right on the center of dilation. Let's say this is point J, and it just so happens to also be the point of dilation. Well, one thing we'll notice is if we look at it, let me delete everything here. Point J does not move. So if a point is right on the center of dilation, it is not moving. Look at K. K is on a line that has the center of dilation, and it just moves horizontally. Or if you look at H, which is on that line, it just moves up and down. So it's either going to move up and down or left and right if it's on the line that contains the center of dilation. If we look at F, for example, it kind of moves diagonally away from it. So what we're going to say for this one is if a point is the center of dilation, so if a point is, and I'm going to use italices, is, just to further emphasize I'm italicizing, is the center of dilation, it does not move. If a point is not the center of dilation, it moves away from the center. That I kind of already said how dilation works. And what if it's on a line that passes through the center? So if a point is on a line containing the center of dilation, what happens? Well, it moves along that line and away. So what I mean by that is, let's take a look at it one more time. Is see how H, this is a straight line, it's moving away from it. And one thing I should say is as I increase it, because if we're decreasing, obviously it moves closer. It does not move away. This one I should say as scale factor increases. You guys can even say the opposite. You can say it moves closer as scale factor decreases. Because if the scale factor is decreasing, it gets closer to the center of dilation. I just like saying away because usually when we use scale factor, it makes it bigger. As scale factor decreases. As always, guys, use the self-evaluation not just as a, oh, I have to do this. Use this as a time to really think about what you've learned from it and what you still might want to learn to understand it better. So moving on to slide 7, properties. So one thing that we learned from that activity should be that slope is preserved. We preserve the slope when we're doing dilation. Slope stays the same, in other words. All right, so here's a question. So we're going to dilate something by 3, 3. What is the slope of this? So here's point B and point C. And if slope is the same, then whatever the slope is for BC, it's going to be the same as B prime, C prime. So let's take a look at this. So if I'm looking at this, I'm like, all right, so let's do my rise. So I'm looking at my Y value. Okay, that goes up. Oops. Let me get rid of that tracking thing. It's annoying. Because I was like, I could have done this with my mouse. So if I go from there, I am going up 5. if I look at my run, my x values, I'm going up by 2. So my slope is 5 over 2. That's all I'm doing. Or 2.5. I'm not sure if this thing is going to want the fraction or the decimal. I'm going to try the decimal first because 5 divided by 2 is 2.5. And it says it's correct. So it looks like we could do that. I'm a little curious to see if it would accept the fraction. Oh no. Let's take a look. 5 divided by 2. Yep. So if you like the fractions, I recommend the fractions. That way you know it's rise over run. It accepts that answer as well. So far we learned that dilation preserves slopes. Now let's study what dilation does for the lengths. All right, so for the lengths, we can already probably guess. It's probably going to make something bigger or smaller. So to make this easier, I'm going to pick only lengths that are away from it. So I'm going to measure the distance or lengths. I'm going to measure this line, and I'm going to measure FE. So FE3, so we're going to go to a half. If we look, let me measure the lines again because now we're measuring the changes. So this one, and this one. We notice that everything got cut in half. So my lines are LK. Oh, I did too many. Oh well. Better too many than too little. IH. I'll say HI just so I can say hi. All right, so we're at 2.2 and 3.2. So 2.2, 3.2. The scale factor was a half. This went down to 1.1. Scale factor was 3.2. That made this go down to 1.6. I'm just calculating based on the fact that it's a half. And if I zoom in here, 1.6, yep. So it got cut in half. So as you guys may guess, if we double the scale factor, this should double the size. So we're just doubling the size. So what's going to happen when we double the scale factor? The size of the original doubles. We get this 4.4. We get this 6.4. If we triple it, we're going to multiply by 3, so 6.6. And we're going to get this 9.3 times 2, 6. Ratio. Well, this ratio means that we're going to do new over old. So we're going to do new over old. Well, 1.1 divided by 2.2, that's just 0.5. Now we're going to do new over old. Well, 4.4 divided by 2.2, that's just 2. And if we do this 6.6, so always remember the ratios are always new over old. We get 6.6 divided by 2.2, that's 3. So you guys can guess that the remaining answers are 0.5, 2, and 3. So that's all we're doing for this one. They're just saying that, hey, the scale factor affects how long it is. Does that make sense, guys? I feel like that should be obvious, but they just want us to prove that. We're basically just copying this part. Everybody good on understanding that? Yes, no, maybe? Cool. All right. The next thing, I always hated the distance formula for geometry. I feel it's a very algebra based concept. The distance formula from geometry comes from the Pythagorean theorem. A squared plus b squared equals c squared. The only thing is, let's pretend we called this a d for distance, the distance between this point and this point. Well, how do we figure out what a is? Well, a is just our x2, this point right here, minus our x1, this point right here. So that's why all of this is technically a squared. Our b, well, this is our y value, we'll call it y2, and this is our other y value, we'll call it y1. So that's our b. Now, why is there a square root? Well, in order to get rid of a squared, we have to square root it. So whenever you guys are scared of this formula, don't be. All it is a Pythagorean theorem. D squared equals a, oh, no square root. A squared plus b squared, which turns into d equals the square root of a squared plus b squared. How do you figure out a? It's our run. A is our run, and b is our rise. That's all it is. That's all the distance formula is. So let's take a look here. Does this formula work? So find the. So we're just gonna do LK, and we're gonna do it at 3. So if I do LK at 3, let me find my L and my K here. So if I look here, I'm not going to do the distance formula. I think it's dumb. I'm going to do this. Oops. Let's see if this works. Nope, I don't know why GeoGebra really hates this. So if I look here, my rise is 6, my run is 3. So when I'm showing my work for this, I'm just going to use the Pythagorean theorem. I'm just going to say d equals the square root of my run was 3 and my rise was 6. So then for my next step, I'm going to do 9 plus 36. And this is going to end up being the square root of 45. You can just leave it like that if you want. If you want to go into a little more detail, factor tree it, 9 and 5. You can take the square root of 9. So you end up getting this 3 square root 5. Let's see what 3 square root 5 is. Oh, not that calculator. No. My computer's going to go all slow because that calculator takes a lot of time to load. I'm going to take the square root of it, and I'm going to multiply it by the 3. I see that I get this 6.7. Okay, so it's a little different than the 6.6 I got before, but I'm sure there's a little bit of round off error on GeoGebra's part. GeoGebra is probably like rounding something off a little bit when it measured the original. I'm sure the original is like 2 point something, 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 which is probably messing it up. Oh, what's going on here? So there's just round off error. So we would say, we would show our work like we did there, this whole idea of square root of 3 squared plus 9 squared. And we would say, for words, we're going to say, it is a little off. And if you guys didn't understand how I did the square root of 49 by factor tree, just do this. Take the square root of 45, you see it's 6.7. It's a little off. 1/10 off to be exact. 1/10. It's off by 1/10, in other words. Meaning GeoGebra might have some round off error. I would blame it on GeoGebra because the distance formula, we learned it in algebra and it works out. With respect to the scale factor of the length, what can we explain? Scale factor is what we multiply the original length by. And another way of saying scale factor remember is what I said, new over old. So new over, I'll call it original just for this sake, is equal to the scale factor. Well, think of it this way. If I switch this, like if I multiply original by both sides, I get original equals, scale factor times original. So scale factor times original equals the new. So that makes sense. If scale factor is new over original, then scale factor is what we multiply the original to get the new one. And then, as always, let me know if you guys were having trouble with this. Is everybody good? Did anybody need me to go over their stuff? I know I use the pen a lot in this. Anybody need me to go over anything? Have any questions on what I answered? Everyone good? Yes, no, maybe? Everyone asleep? It's all good? All right, cool. Thanks. All right, let's take a look here. So here they're just going to talk about ratios. This idea like if we cut this square in half, then every side's going to be cut in half. Pretty basic. Basically, the scale factor is what we multiply by. The scale factor is 1/2. So everything gets cut in half. That's what they're saying right here. Length of dilated length is scale factor times length of original. Just think scale factor times old equals new. Or you can think of it as new divided by old equals scale factor. That's all we're doing with scale factor. All right. So they want us to use the distance formula again. Again, guys, I'm not the biggest fan of the distance formula. We spend all this time teaching you guys how to use the Pythagorean Theorem, and when it comes down to like when we can use it, they're busy trying to teach you a completely different formula. Forget all that. Let's make this easy. What's my rise? Well, if I'm going from -7, I have to cross 0. So I go from 7 and then I have to move another 8. So my rise is 15. My run is 8. All right. So that's it. So I'm going to do 15 for my oops, wrong one. 15 was my rise. So 15 is my rise. I used the right color. I just circled the wrong things. And then my run was 8. So I'm going to say 8 squared plus 15 squared. And we're going to take the square root of all that. And that's going to give me my D. So I'm going to get 64 plus, I randomly remember this from a Batman Beyond cartoon, but 15 times 15 is 225. Remember, it's an episode where Terry is trying to say that he memorized the mathematics tables. So 15 times 15 is 225. If you guys don't remember it, don't worry about it. That's what calculators are for. So we have 9. 4 plus 9. 2 plus that is 8. So 289. Let's see if that has a really nice square root. I'm assuming it does. Otherwise, GeoGebra is just mean. Yep, 17. So our answer should be 17. That's it. What? No way. Incorrect. Oh, they dilated it by 2. That's me not reading the problem, guys. They dilated by 2, which means I have to increase this distance. 17 times 2, 14. 7 times 2 is 14. Let me kind of show you how I'm going to do this. 17 times 2 is 14. 10 times 2 is 20. So that's how I know that this is 34. That's an easier way to kind of think of multiplication. If you guys have trouble with multiplication, instead of thinking this, think this. Oops. This allows you to kind of think of this a lot faster. All right, cool. That was me not reading. All right, and then just remember your summary. So remember, slope stays the same. And the big idea here is old times scale factor equals the new length. That's the main idea. And they talk about how we use this in everyday life. Like if we're drawing stuff, you saw the logo being bigger or smaller. Graphic designers are always making things bigger and smaller. All right, so we had enough time to finish the whole unit right on time. If you guys haven't answered the question of the day yet, it was what is your favorite midnight snack?